So, good morning, everyone. We are still in the morning, right? So, I would like to first take the opportunity to thank the organizers for organizing such a nice conference. I think the small number of audience is just nice to make me nervous because there's a maximum there's a kind of optimal number of audience that makes me most nervous is about this size. So, okay, today I'll talk about tree size, complexity, and quantum computation. So the complexity I'll be talking about is in a slightly different flavor than the complexity that all the previous speaker has talked about epsilon machines. Because I think to me those complexity is a complex process. So we're trying to characterize how complex the process is. But here I want to talk about the complexity of a state. It's something more static, something more like kinematic rather than dynamical. So, and then I'll discuss the relation between this state complexity and quantum computation. Okay, I start off by saying that this is a joint work with our ex-postdoc Nguyen and Valerio Scarani, who's my PhD supervisor from CQT as well. Okay, so let me start off by telling you the motivation of studying this. So one of the motivation is rather foundational. So because recent years people have been, especially the experimentalists, they have been trying very hard to approach what is a Schrodinger's cat. So they are creating superposition of larger and larger size, like whichever their favorite size measure is. And then in the hope of testing, okay, will the principle of superposition break down if we put larger and larger object into superposition? No? But so far, I think all the evidence is no. Like we can put pretty big objects into superposition right now. But what we are thinking is, even though all these superposition are of large size, maybe involve large mass, a huge number of particles, but they are of a simple type. So the state in superposition is rather simple. So instead of testing the principle of superposition in a larger and larger superposition, can we ask the question, can we create more and more complex superpositions? So in order to test this idea, we need to propose a measure of complexity of states. And second is maybe we can view this complexity as a boundary between quantum and classical. No? So is complexity a key feature that distinguishes quantum states from classical states? And the second part of our motivation is very similar to what Dex on Monday talked about. So we know, we believe quantum computers are more powerful than classical ones. But what is the precise ingredient in quantum mechanics that empowers us with quantum supremacy, if it exists? So there are many candidates. The first one, I think, is just superposition and interference. So with just superposition alone, maybe people will propose what is called quantum parallelism. So it says the advantage of quantum mechanics is like we can try all the possible solution at the same time in a superposition. That's why we are performing better than classical physics. But I think this cannot be true, because if that is the case, we would have an advantage in all kind of algorithm. But so far, we only have good quantum algorithms for a very restricted class of problems. So this naive way of thinking, trying all the possible solution at one go, is definitely not right. Or at least we need to refine the idea. So a slightly improved of this is maybe we can perform better in those problems where the best solutions miraculously cancels each other in an interference manner, and only left with good solutions. So that's the idea of maybe interference is a key that gives us the power of quantum computing. And next, that is everywhere and is almost a key in all the quantum strangeness is entanglement. So is entanglement the key feature of quantum mechanics that gives us the power in quantum computation? And the answer is complicated. So I put several references here, and they have even contradictory sounding conclusions. So the first one says if the entanglement is small across all the bipartitions, then so if entanglement is small, we can simulate this quantum computation efficiently with a classical computer. The second paper says, from Van der Nest, says some computations are hard to simulate classically, even though the entanglement is arbitrarily small. So actually, there's no contradiction because they're choosing different measures of entanglement. Especially the first one is Vidal has chosen a discrete measure of entanglement, and Van der Nest has chosen a continuous one. And then the third one is even a little counterintuitive. So it says, if we have too much entanglement in the state, maybe this state is not so useful for measurement-based quantum computing because the entanglement is so much that using this state as a resource state for measurement-based quantum computing is as good as flipping a random coin. So there's like too much randomness in your state. Okay, so I would say the relation between entanglement and quantum computation is a bit complicated. Like, it's definitely necessary, but it's far from sufficient. And also, like another very simple example is the Gottesman-New theorem. So we can have a even global entanglement across a super large state, but still, like if you remember from Deck's talk, we can simulate any Clifford circuit efficiently with a classical computer. All right, and the next candidate is Discord. So people have also shown that even with one qubit, so the one DQC model, and there is something that is hard to simulate with a classical computer, even though there's like no entanglement, but only Discord is present. Okay, and here in this talk, I would like to present one more candidate, which is complexity. To be more precise, the complexity of quantum state as like a feature of quantum mechanics that kind of give us the power in quantum computing. All right, and so throughout this conference, we have saw different definition of complexity, like in different flavors. But I think there's something in common. So one, I think also Daniel showed us the picture of the coffee just now. So complexity is definitely something like, let's say this is the axis of orderedness. No, on one hand is the completely ordered stuff, like you can think of a crystal, or you can think of maybe the product state of all zeros. And then on the other hand, it's like gas. It's very, very disordered. And for quantum states, maybe you can think of the completely mixed state, or maybe even a maximally entangled state. So these two ends of this axis somehow correspond to low complexity. And what is in the middle is like human beings like us, our brain, or life in general. Those are somewhere in the middle of orderedness and disordered. So that is one common feature in all the complexity, definition of complexity that I learned in this conference. And the second is maybe a little bit tautology. So I think complexity is a measure of resource. So if you talk about computational complexity, maybe it's a measure of how much time you need to do some computation, how much space you need to do some computation. And then for communication complexity, it's like how much communication you need. And for state complexity, I would rather think like, what is the resource required to produce the state? Or in another way is how much resource is required to simulate the state. So these are the two kind of resource that I have in mind talking about this state complexity. All right. So there are different state complexity measures, so as opposed to process complexity measures, which is more related to the epsilon machine work. There are several state complexity measures, like for example, the quantum generalization to the Kolmogorov complexity and the circuit complexity. So the first two are more related to what I see as the preparation complexity. And the third one that I'll be focusing on is more like simulation complexity. And I'll tell you more about, once I tell you the definition of tree size, you can see how it is related to simulating a quantum state, weakly simulating a quantum state with a classical computer. Okay, so tree size complexity will be my focus of this talk. All right. So I think Vlaco also mentioned yesterday, somehow some complexity measure are theory dependent, right? So depending on whether you use a quantum description or classical description, the complexity might be different. And here is like a map of complexity over here. So on the one axis, we can think of a circuit complexity or generation complexity, and on the other hand, we can on the other axis, we think of a simulation complexity. And then we ask the question: so where are those states that are useful for quantum computation should lie in? So definitely, it's not in the first corner. So those will be the state. Although it's easy to generate quantum mechanically, but it's also easy to simulate it with classical computer. So you don't expect those states that will give you any advantage in quantum computing. And then probably this sector doesn't exist because all the quantum mechanics can simulate classical mechanics.
Since we've been talking about simulation before, but just one quick clarification. Here, simulation
Weakly.
means you can reproduce the statistical behavior.
You can sample the classical, the statistical behavior. Okay, so probably that sector doesn't exist. And then in the last lower right corner over here, it's probably not useful. So if some state, even though it's very hard to simulate classically, but it's also very difficult to generate it with quantum mechanics, then it will also take you a lot of resource to even create those states. So they can't be useful. So what we're looking at is those states that are very difficult to simulate, but they are rather easy to produce quantum mechanically. So that's the state that we'll be looking at. And the simulation complexity here, we'll try to use tree size to capture this. Okay. Yeah. How much time do I have?
Don't worry.
Okay.
We let you listen to this mistake.
Okay.
I'll give you a warning at 5 minutes.
Okay. Okay, so now let me introduce this tree size complexity measure. So it's proposed by Scott Aronson. So he's been mentioned the second time today. Okay, so what is this, no? So it's a state complexity measure for n qubit pure n qubit states. All right. So in general, to describe n qubit pure state, we can naively write the state in the computational basis. So you have 2 to the power of n terms, and each term in front of each term we write down the corresponding amplitude with one complex number. But is this the most efficient way? So maybe there's a more efficient way. So let me introduce the tree representation of a quantum state. Basically, we construct a tree where at the root or at the nodes of the trees, we put either a plus gate or a tensor gate to represent superposition and also joining of qubits respectively. And then on the very bottom, okay, so those are, if you turn it around, those are the leaves of the tree. So that's why we have an inverted tree. So on the leaves of the trees, we put some single qubit cats. And the goal of this practice is, let's try to represent the state with a tree of a smaller size, where the size here means the number of leaves. And the freedom you have is any single qubit rotation. So you can have a different cat here on different branch of the tree. So you have that freedom. And the goal is to minimize the number of leaves in the end to write down the state. Okay, so and as promised, I need to tell you why is this a good way of looking at simulation complexity. You know? So in order to write down the state, so before simulating the state, you need to record the state. So this tree size here captures how many cats you need to remember. So for each cat, you need to specify what state it is. And also this will tell you how many amplitude you need to record in order to write down the states. Because we are going to write down the amplitude of each superposition on the branch where there's a plus gate. So in the end, this the tree size of a quantum state is related to like the number of real numbers we need to write down in order to record the state. And that gives us some idea on how to simulate the state or simulate the computation associated with the state.
This is dependent on the choice of local basis, right? Is it?
So you have the freedom to choose any local basis.
That will be invariant. The measure is invariant with respect to choice of local basis.
No, you try to apply any local unitary in order to minimize the size of the tree.
So you minimum. Okay.
Okay, so
But once you've chosen a basis of a particular qubit, that applies across the whole tree.
no. So each part, like for example, I can choose one basis here for this 0 and 1. I can choose another basis for, even though they correspond to the same qubit.
They're just products.
So, sorry, in
They're just arbitrary pure states, in fact, not necessarily 0 and 1. They're arbitrary pure states.
yes, arbitrary pure state. So I'll show you an example in the next slides. Maybe that will be clearer. Okay, so the tree size is defined as the size of the tree in the minimal representation of a quantum state. Okay, so what is fixed is the notion of separation of qubits. Because if you don't have this notion, then I can always write it in just one single cap. So that kind of makes it trivial. All right. So next, I'll just like to make the definition clearer. I'll show you how to trim a tree of 3 qubits. Okay, so first let's write the most naive way is to represent it with 8 cats because you have 8 computational bases. And then the next, not so naive decomposition, maybe we can do a repeated Schmidt decomposition. So what does it mean? So we first treat the first particle as one party, the second and third particle as another party. So you can factorize out the 0 of the first particle, the 1 of the first particle, and then left with a generic 2-qubit state of the second and third particle inside the bracket. And then we can do a Schmidt decomposition of those 2 states. So by doing this, we can write the state with a tree with 10 leaves. But this is still not the optimal because people in characterizing SLOCC equivalent classes have come up with an even simpler way of writing a 3-qubit state called I call it the Essine decomposition because it's proposed by Essine et al. So you can write down actually any 3-qubit states with at most 8 leaves in this way. So here you can see that in different parts of the trees, I can use a different basis. So here on the third qubit, I'm using this double prime basis, but here I'm using 0. So we do have this freedom. So as you can see, finding the minimum tree of a state is not a trivial task. So maybe for a few qubits, you can exhaust all the SLOCC equivalent classes, but for more qubits, actually we don't know how to do that. There's no algorithm.
So is this a topological property in that it doesn't really matter what the probabilities of the states are in this to get it? Because you're only really concerned with the number of parameters rather than sort of the values that these parameters might take? Or
Yes. Yes, so the ABCs, I don't care what the values of the ABCs are. But
as long as they're not 0.
yes, as long as it's not 0. Sorry.
Minimum unique.
Is the minimum unique? It has to be no, because you can always exhaust all the possibilities and.
There's sort of lessons from the automata theory in the 60s where you can look at regular grammar for finite state machines.
Mm-hmm.
Using the regular grammar complexity, number of terms in your regular expression is not a unique measure of complexity. It's not correlated, for example, with the memory in the equivalent finite state machine. And for example, measures like star height, which is a parsing, it's not a consistent complexity measure. So
Okay.
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 Well, they're different parsings, right? So it turns out you can parse it. I'm just saying in a case where you can calibrate what you sort of think the amount of state information is automaton provides a nice linear order of memory. When we look at the corresponding grammatical measures, the same regular language, there's measures on grammatical expressions. These functions, it's not consistent. And this is well known, in fact, in the 60s, that you have to be careful
Okay. Okay. So
So that's why you have to show uniqueness to it.
I have no proof of uniqueness, but it will not be essential in the later part of the talk because what we are aiming at is to prove a lower bound on the tree size. And so maybe after that, see
Well, you
if
should look into, so,
Yeah,
search
yeah.
on star height.
star height.
representations,
Okay.
And that you'll find this problem. Maybe it's different, I don't know.
Thank you. Yeah, thank you for pointing out that.
How to measure the tree size? Does it depend on the number of leaves or the depth?
The definition is the number of leaves. So, like in this case, you have 1, 2, 3, 4, 5, 6, 7, 8. Right. So it's just a number of leaves, and it's also if you enforce it to be a binary tree, then there's a linear relation between the height and the number of leaves also. Okay. So now as I say, what we are more interested is a lower bound. So, and we are interested in the case of many qubits. So in order to talk about whether a state is complex or simple in this measure of complexity, we need a family of states indexed by the number of qubits n. And we say the state is complex whenever the tree size scales super polynomially with the number n. So in order to show a state is simple because you just need to show a polynomial tree representation of that state. Because any size of the tree representation is the upper bound of the real tree size. In order to give you some example of simple states, for example, the GZ state, people think it as a good representative of the Schrodinger cat because you have 0, 0, 0, 0 plus 1, 1, 1, 1 is like live cell, so plus a dead cell that forms a cat. But it has tree size linear in n, so it's rather simple because linear is the smallest you can get. Even for product state is n. And the second example is a decay state. A decay state is a equal superposition of qubits with a fixed Hamming weight. Like for example, you can have a 100 plus 010 plus 001. This is a decay state. And the third example is the matrix product state with rank chi. So depending on whether this chi increase with the number of qubits, it can be simple or complex. But let's say chi is a constant, no matter constant with respect to the number of qubits, then this is just polynomial in n. So that's why it's a simple state. So maybe just show you a little bit more detail in how to prove this relation, this tree size for the matrix product state. So let's assume for simplicity we have 2 to the power of k qubits. 2 minutes? Okay. I thought you said you tell me when there's 5 minutes. Okay, so this is one way of representing the matrix product state, right? So now the smart idea is to insert a identity in the middle of the matrices, and the identity of a D by D matrix can be represented by a sum of D terms, basically. And then here, basically, you separate it into 2 shorter matrix product states with a length with a number of qubits n over 2, but at the price of having a sum over D terms. So you can do this repeatedly or k times, where k is just log n. So in the end, you have the tree size is smaller than 2D, or 2D terms, 2D to the power of log n. And then you can rewrite this as n to the power of log d, where d here is the size of the matrix in the matrix product state representation. So hence, if d is a constant with respect to n, then tree size is polynomial. For example, the 1D cluster state, you can represent it with a size 2 matrix, and hence it only have a tree size of the order of n squared. Okay, I'll speed up. So in order to prove a lower bound, we rely on the result of a result on the formula size of multilinear formula. So multilinear formula just means it's a formula that is linear in all its inputs. So as you can see, for any quantum state, we can just associate it with a linear formula by replacing 0 with, for example, 1 minus x and 1 with x. And then here, oh, sorry, I forgot to mention. So the multilinear formula basically is the fx, such that you can write the state as f with your x and the cat x. So that's the associated linear formula with the quantum state. And a result by a mathematician, Ras, says something about the linear formula, but I will phrase it in quantum mechanical terms, with quantum information terms. So for a pure state of n qubits, consider all the uniform half-half partition of the states. If over all this bipartition of the states, the probability of the Schmidt rank across this bipartition is larger than this number, so the full rank is 2 to the power of n half. So the Schmidt rank is rather large for not so small probability. If it satisfies this condition, then tree size must be of this order, so at least as n to the power of log n. So this is, I think people call it quasi-polynomial, so it's faster than any polynomial, but it's much slower than exponential. So this is how we show a lower bound on tree size. So you can see this, what does it mean? Like this bipartition, so you have n particles, and no matter how you cut these n particles into n half and n half, somehow the chance that a large entanglement remains is high. So you can somehow feel like the state is complex in that sense. Okay, and then here are some examples of complex states, which I'll skip, but I'll try to point your attention at the subgroup states, because the 2D cluster state, which is known as a universal resource for measurement-based quantum computing, is complex, is included in this subgroup state. And then can also be witnessed efficiently. Okay, so in the case, so finally I have to discuss the relation. Okay, give me 1 more minute. The relation between state complexity and quantum computation. So I want you to remember one thing is super polynomial tree size is essential in the initial resource state for MBQC. If not, the MBQC can be simulated efficiently classically. Okay.